do a few examples of combination problems. So using this formula here, we will set them up. I'm not going to be so much interested in running the calculation at the end, but just setting up the problem correctly with the right value of n and k. Now on the homework, of course, the challenge is going to be deciding whether each question is a permutation question or a combination question. And again, you'll just think about whether order is significant or not, whether all you're worried about is the ones that you select. So let me show you a few examples. Really simply, let's take an example where we calculate, for instance, 8 choose 5. Again, using the formula, that would be 8 factorial divided by 8 minus 5, or 3 factorial, and 5 factorial, which turns out to be 56, in case you're interested. But let's say, for example, we have a standard 52 card deck, and we want to know how many ways you can get a hand of 5 cards, how many different hands you can draw out of a deck of 52 cards. Again, without too much trouble, you should be able to tell that this is a combination problem. You don't care what order the cards are dealt to you. All you care about is which cards you end up with at the end of the process. So it's out of a group of 52, we're choosing 5 cards, or you could write combinations with 52 and 5. And of course, this works out to be 52 factorial over the difference between 52 and 5, which is 47 factorial and 5 factorial. If you want to do these by hand, let me show you a little shortcut here to save you some time if you need to type this in or write it more simply. So if we start writing this out, 52 factorial looks like this. And I'm not going to write out the whole thing, but notice that after 48, the remainder of it is really just 47 factorial, right? So it's like there's the entire string of 52 factorial, but after we write down the first few terms, everything from this point on is equivalent to 47 factorial, so we kind of chop off that tail. Now why did I stop there? Well, because we have 47 factorial in the denominator, and so those two will cancel each other. So we can cancel this and this, and so the problem works out to be 52 times 51 times 50 times 49 times 48 divided by 5 factorial. Now why do I show you this? It's just kind of nice if you can simplify problems like this sometimes to make your life easier. There are also cases where you might have a calculator that doesn't have a built-in combinations formula, and if you try to enter 52 factorial, most calculators will refuse to give you an answer because the number is too large. So by doing this, you can cut it down to a manageable size number, and you can find the answer. In case you're interested, the answer here is about 2.5 million, closer to 2.6 million. That's the number of 5 card hands that you can be dealt from a 52 card deck. So if you ever look up probabilities for poker hands, you'll notice that the denominators for those all look like this because you're counting out of the chances that you're drawing 5 cards out of a total 52 card deck. Here's another example. This one's going to combine the combination problem with something we've done before. So let's say in a college or university, let's say the math department has 9 faculty members and the computer science department has 11 faculty members. And let's say we're going to select a committee for a discrete math class. So the committee is going to be chosen from these 2 departments to get a wide range of views, and we want to select a committee with 3 math faculty and 4 computer science faculty. So that's the makeup of the committee, and the question is, how many ways can we make that happen? If you think about it for a minute, we can kind of break this problem into 2 pieces. So to begin with, there are basically 2 choices to make. We have to pick the math faculty and we have to pick the computer science faculty. And it turns out this is just a product rule, isn't it? Once you've selected the number of ways to pick the math faculty, and you've selected the number of ways to pick the computer science faculty, if you multiply those two together, that'll be your final answer. So that's kind of the key to this question, is noticing that it's a product rule question at its core, that we're dealing with the number of ways to do two things in order, selecting math and then computer science faculty. And within each of those, it turns into a combination problem. So you'll see some questions on the homework and the test where you might need to use more than one type of method, and being able to break down a problem like this is important. So once we know that it's a product of those two things, that we're looking for the number of ways to select 3 math and 4 computer science faculty using the product rule, then selecting the math faculty, well, there are 9 to choose from, and we're selecting 3. And then the computer science faculty, there are 11 to choose from, and we're choosing 4. So the answer is going to be 9 choose 3 times 11 choose 4. And so if you're interested, 9 choose 3 is 84, and 11 choose 4 is 330. And the product of those works out to be 27,720. Again, the final number is not the important piece. The important piece is that you can break down a problem like this into simpler pieces. We can work a similar one as well. So the next one I'm going to show you, instead of using the product rule with combinations in each piece, we're going to use the addition rule with combinations in each piece. So this AND rule, or the AND question, is basically going to change into an OR question. Now the way it's set up is a little bit confusing at first, but see if you can follow this. So it starts out simple enough. We've got a group of 12 people, and we're going to select a team of 5 people. Now here's the twist. The twist is that 2 people in this group insist on being together. In other words, either both of them are on the team or neither of them are on the team. So if they're not both going to be on the team, they don't either want to be on the team. Which again sounds complicated, but once you recognize that it's an OR question, then you can deal with each part separately. So we can ask the question, well, how many ways are there to select a team of 5 if both of them are on this team? And then we can say, how many ways are there to select a team of 5 if neither are on the team? And add those two together, and we'll be done. So if we can figure out, again, number of ways where both are on the team, and then the number of ways where neither are on the team, then we can add those two answers together. Let's take the example where neither are on the team first, because that's going to be easier. If neither of them are on the team, you can think about, we're still selecting 5 people, but now how many do we have to choose from? And again, you might want to pause the video and answer that for yourself and see if you're right. But if we're selecting from a group of 12 people, but these 2 people are not going to be selected, then we're really only choosing out of 10 people. We're really only choosing our 5 team members from a smaller pool of 10 if we know that these 2 are not going to be on the team. So we have 10 now to choose from, and we're selecting 5. So you have 10 choose 5. With that in mind, now we can go to the other side, where we're selecting the number of ways to get them both on the team. And again, this might sound complicated, but if you think carefully about it, you'll realize that now we are really only selecting 3 people. Because if they're both on the team, we don't have to ask the question of, we don't have to deal with them getting on the team. We know that they're on the team, and there are only 3 spots left to be filled, so 3 people to be chosen, and again, there are 10 people to choose from, because our 2 people we're dealing with are already on the team. And so there's 10 people to choose from, and we're selecting 3. So this is an example, again, of a problem that sounds hard at first, but if you think about it the right way, if you look at this carefully and say, well, there's an OR question, so we're going to add together the number of ways of doing each individually, And then think carefully about what each of those situations implies, whether they're both on the team or neither on the team. What does that imply about how many we have to choose from and how many we're selecting? So if you can do that, then you can break this problem down into a situation like this. So again, on the homework, you might see ones like this where you need to split up a situation into two separate pieces and break them down individually. So again, just to give you the numbers on this, the first part, 10 choose 3, is 120. The second part, 10 choose 5, is 252. And you can use these, do these on your calculator just to practice and make sure you get the same values. So this works out to 372. One more example I want to show you, which again, you'll see ones like this on the homework, although it may be disguised a little bit. But if you look carefully, you should notice a homework question or two that looks like this. The question starts out this way. We're going to flip a coin 6 times. And when we flip a coin, we have 2 possibilities each time, right? We have heads and we have tails. So there are 2 options each time you flip a coin. The question is, if we do this, how many ways could we do this and get exactly 2 heads? So how many possible arrangements or how many possible outcomes of this experiment contain exactly 2 heads? Now, if you start thinking about this, you can kind of get yourself wrapped up in the complexity of it. You could say, well, I could have 2 heads, I could have more than 2 heads. These heads can come in any position here, right? So there's lots of options where this could go. And again, you could sort of spend more time on this than you need to. But if you think about the question the right way, you can get to the answer much more quickly. So in case you want to pause the video and try this on your own, think about how you can use combinations to do this. So to use combinations, think about what we're looking for here. We have 6 results, 6 coin flips, and we want to know how many of those contain exactly 2 heads. We don't care where those occur in this listing. All we care about is selecting 2 of them, any 2 of them, to be the ones that get a head and the other ones get a tail, right? So all we're looking for is selecting 2 out of these 6 positions. And once you recognize that, it's pretty easily a combination problem. So we've got 6 coin flips to choose from, and we're going to select 2 of them to come up heads. And so it's just 6 choose 2, and that's all it is. So it sounds harder than it is. Once you recognize the type of problem that it is, it's relatively straightforward. So 6 choose 2, in case you're interested, again, is 15. But as always, the setup is the hard part, and it's the part that we're more interested in.